So welcome to what is the second of three videos or lessons on transition metals. And the focus of this lesson is going to be to understand what we mean by a transition metal complex, and then the rules of how to name a transition metal complex, which itself is quite complex. So what we mean is something that looks like this, where we have a transition metal at the center, and around it we have different molecules or ions that are bonding to it. And transition metal complexes are usually drawn with square brackets around them, and the charge can either go inside or outside the bracket. Ideally, it's probably outside the bracket, so this is not the best example. But they have a transition metal at the center. In case you weren't aware, it's cobalt in this one, and then we have ligands around it. Now the ligands can be negative ions or neutral molecules. Because transition metals are usually positively charged, positive ions do not tend to form ligands because like charges repel. But neutral and negative ions surround it. Now, a ligand is just the term we give to anything that will have a non-bonding pair of electrons. So two electrons that are not involved in a bond attached to one of the atoms. And what happens is that that non-bonding pair of electrons comes from one of the atoms in a ligand and gets donated to the metal. So in the end, we have a bond that has two electrons in it, like a normal bond, but both of those electrons came from the same atom. And that type of one-sided sharing of electrons is what we call a dative covalent bond. Sometimes if you're reading in other sources, you may see it called a coordinative bond. But the term that we're really looking you to use is a dative covalent bond. Now you can see in the diagram on this slide that they've used normal bond lines to show the bonds. Dative covalent bonds are sometimes shown as arrows, and the arrow goes from the ligand to the metal, representing that the electrons are being shared from the ligand onto the metal. So if you see arrows, that's all that means, and it just is the same thing as having a normal bond. So it's dative covalent bonds. Now, there are lots of common ligands that are found on transition metal complexes. So neutral molecules like water and ammonia are very common, but also negative ions like cyanide, hydroxide, and any of the halides, so chloride, fluoride, bromide, etc. Now, each of those ligands in that list are described as being monodentate, and that means that they can only form one bond to the transition metal. However, there are some ligands that are able to form more than one bond. A good example of this is oxalate. Now, oxalate, you can see on that diagram, there are two oxygens that are forming double bonds, and then we have two oxygens that are negatively charged. It's the ones that are negatively charged that would bond to the transition metal. So here's a diagram of what it would look like. So it's bonding to a tin in this case, and it would be described as bidentate, meaning that it can form two bonds. So denticity is the number of bonds that a ligand can make to a metal. It comes from the same word as dentistry, and it means teeth essentially. So if something is monodentate, that means it's one-toothed. Bidentate rather than didentate. I'm sorry, there's a spelling mistake there. But bidentate, meaning two teeth, tri, three, tetra, four, penta, and hexa. You will, in Unit 3, you'll probably encounter ethylene diamine tetraacetic acid, EDTA, which is a common hexadentate ligand which coordinates like this. So you can see whenever it forms the complex, the hydrogens on each of the carboxylic acid groups come off, and it is the O- ions that coordinate to the metal, but also the two nitrogens also have lone pairs, and coordinate to that metal. And EDTA is often used to coordinate to two transition metals and is often used as a medical treatment if someone has poisoning. So lead poisoning, mercury poisoning, anything like that, EDTA can be given to the patient. And what happens is that it forms a complex to the metal and allows you to extract it, and it makes it less harmful. Now, how complexes are written or drawn, as I said before, whenever they're drawn, we put square brackets around them, but also whenever we're writing out the chemical formula, we put the chemical formula of a complex inside square brackets. Now, typically for a complex, the transition metal is written first and then the ligands come after. If the complex is charged, which it often is, the charge goes outside the brackets. If you have a ligand that is got multiple atoms in it, like water or ammonia, to represent if there's more than one of those, it gets put in brackets. So you can see in that first example, copper with 6 waters, the water is put in brackets so that we can put the number 6 after it. Whereas chloride in the second example, the 4 is not, there's no brackets around the chloride because that 4 is rightly just telling us that there are 4 chlorides. So you've got to be careful of when to use brackets and when you don't need to use brackets. Now, coordination number, this is kind of related to denticity. Denticity was a way of describing the ligands. Coordination number is a way of describing the metal. And it's basically how many dative covalent bonds are around a metal. And it is going to be the sum of all the denticities of the ligands around it. So in that first example, we have got iron with 2 chlorides and 2 cyanide groups around it. Chloride and cyanide are all monodentate, so the coordination number, Cn, is 4. The second one, nickel, OX is sometimes a shortened version of oxalate. However, oxalate is sometimes written C2O4, so just be careful there. But nickel oxalate is a bidentate ligand, and there are 3 oxalates, so that gives a coordination number of 6. So now I've got 4 examples here. Now it's your opportunity to pause the video and try and work out the coordination number of these 4 different examples. So if you want to pause the video now, have a go, and when you replay or press play, you will get the answers. Okay, so welcome back. If you took the opportunity to do that. If you didn't, you just got to hear me take a really long pause. But the first one is a coordination number of 6. That's because water and cyanide are both monodentate ligands. There are 2 waters, 4 cyanides. Together that makes a coordination number of 6. The next one is the manganese pentachloride. And there are 5 chlorides around it. Each chloride is monodentate, so it's got a coordination number of 5. The next one, the nickel oxalate with ammonia around it, has a coordination number of 4. The oxalate is bidentate, and the ammonia, each one of those is monodentate. So bidentate plus 2 monodentate gives us 4. And finally, we've got an EDTA. An EDTA was a hexadentate ligand, so the coordination number is 6. Usually the coordination number for first row transition metals does not get any larger than 6. However, as you move down the periodic table, coordination numbers can get as large as 12 for some of the biggest atoms. But you would be expecting nothing more than 6 really for the first row transition metals. So now we're going to get into how to name a transition metal complex, and there are lots of rules and it does take time. However, it is logical once you have learnt the rules. So there are 5 parts. So the first rule only applies if the transition metal complex is part of a compound. So for example, if you've got a transition metal complex that has a positive charge and if it's forming a compound, it would need to associate with ions that are negatively charged. And if the transition metal complex is negatively charged, it would need to form a compound with things that are positively charged. When that's the case, when it comes to naming a compound, the positive ion is always named before the negative ion. So if the complex is negatively charged, it's going to go at the end of the name. If the complex is positively charged, it's going to be the first part of the name. So the second thing is, how do we name the ligands? And you will see that the ligands, their names change to denote that they are part of a complex. Then what we do is we use prefixes to describe how many of each ligand there are. So these are going to be your bi, tri, tetra, etc. Prefixes. Then the metal. So the name of the metal will change. How we describe the metal changes depending on whether the complex is positive or negatively charged. And finally, Roman numerals are put at the end of every complex to indicate the oxidation state or the oxidation number of the metal. And here is an example, just so you can see. Now this is a transition metal complex on its own, not part of a compound, so we're ignoring the first rule. But that is called diaqua tetrachlorido cobaltate 2. So you can see it is quite complex. So what we'll do is we'll build it up step by step. So the first thing we'll look at are the names of ligands. So I've got a list of the ligands that you would be expected to know in advanced higher. So we've got water, ammonia, chloride, cyanide, hydroxide, oxalate, carbon monoxide, and oxide. And we've got how that name gets translated to describe that it's in a transition metal complex. So water becomes aqua, ammonia becomes amine. Now with ammonia, it's really important that you include that double M, because an amine with one M is another type of chemical that you're going to learn about in Unit 2. So you need to put that double M to make sure that it's ammonia. I'm going to skip the next ones and I'm going to actually go down to carbon monoxide, and carbon monoxide changes to carbonyl. Now water, ammonia and carbon monoxide are all neutral molecules, and you can see for those neutral molecules their name completely changes. Water to aqua, ammonia to amine, carbon monoxide to carbonyl. Those ones you really just have to know. For the other ones, chloride, cyanide, hydroxide, oxalate and oxide, ones that are negatively charged, the only thing you need to remember with those is you change the last letter from an E to an O. So chloride becomes chlorido, cyanide, cyanido, hydroxide, hydroxido, oxalate, oxalato or oxalato, and oxide to oxido. So the neutral molecules, their names completely change, and you have to remember water is aqua, ammonia is amine, carbon monoxide is carbonyl, but the other ones that are negatively charged ligands, all you need to do is change the last letter from an E to an O. And then when it comes to having more than one type of ligand in a transition metal complex, you organize them alphabetically. So amine will always come before carbonyl, hydroxido will always come before oxido. They always go alphabetical. The next rule is the ligand prefixes. So if we have more than one of a type of ligand within it, we need to denote that. And what we do is we add a prefix in front of the name of the ligand. So 2 is di, 3 is tri, 4 is tetra, 5 is penta, and 6 is hexa. Now what you need to notice here is 2 is di inside a ligand. But remember, if a ligand can coordinate through 2 points, it's called bidentate. But if there's 2 within a compound, it's di. So try not to get bi and di confused, because it can be, because they're both related to transition metal complexes. But if it's two inside a complex, it's di. Now these ones, it doesn't matter what order these are alphabetically, it is the ligand it is associated with that determines the order. So for example, if you had 3 water molecules and 2 chlorides, it would be triaqua dichlorido, because aqua comes before chlorido. Also, it's going to look odd because a lot of the ligands start with vowels and all of these prefixes end in vowels, so it is often the case that you get a double vowel. So hexaaqua has 2 A's. You have to make sure you put them both. These rules need to be followed really strictly in order to get the marks. They're not very forgiving. Now the third rule is naming the metal. Now the good news is that the name of the metal doesn't change if your complex is positively charged or if it's neutral. So if the square brackets describing your complex has a positive charge outside of it, aluminium is aluminium, vanadium is vanadium, chromium is chromium, iron is iron, cobalt is cobalt, etc. However, a lot of transition metal complexes are negatively charged, and if it is negatively charged, the metal name changes. Now, when it comes to metals that end in IUM, if they're part of a negative complex, all you do is change the IUM to ATE. So aluminium becomes aluminate or aluminate, vanadium, vanadate, chromium, chromate. So you're changing the IUM to ATE. All the other ones, you still end with ATE. But what happens, for some reason that I'm not sure of why, whenever they're in negative complexes, they take on their old Latin names. So iron becomes ferrate. So the Fe is the symbol for iron, and that's where we get ferrate from. Cobalt, all that happens with cobalt, it doesn't end in IUM, but what happens is we just add ATE onto the end of the name, so cobaltate. Copper becomes cuprate, and you can see that's where we get the Cu for copper. And lead, which is a rare one that they would use, but lead becomes plumbate, and that's where we get the Pb from lead, because the Latin name for lead is plumbum, which is where we get the word plumber, because pipes used to be made of lead. So it's only if the complex is negative that we have to use these new forms with the end in ATE. And unfortunately, you just have to learn ferrate, cuprate, and plumbate. The fourth thing is at the very end, what you need to do is work out the oxidation state of the metal, and you do that looking at the charge of the transition metal complex and at the ligands inside it. So a lot of the ligands will be neutral, so water, ammonia, carbonyl, they don't do anything to the oxidation state. But you'll have a lot of negative ones, halides, etc., so they will contribute negatively to the charge of the complex, and you have to sort of use algebra, sorry, to work out what the charge of the transition metal is. Just in the way that in the previous set of lessons you worked at oxidation state for a transition metal. It's just doing that. So here are 4 for you to have a go at. These are complexes that are not part of compounds. So again, if you would like to pause and then have a go at naming these, and I will join you after you've had a go at that. Okay, so hopefully you've had a chance to have a go at these. So here we see. So the first one It's aluminium, it's got water and it's got hydroxides, so it's going to be an aqua and a hydroxido. It's also negatively charged, so that means that aluminium is going to need to change its name. So what we have is diaqua tetrahydroxido, remember alphabetical order, aqua before hydroxido. It's negatively charged, so it's aluminate, and it's aluminate 3 because the overall complex has a negative charge, -1. Water has no charge whatsoever, so we can ignore it whenever we're doing our calculations. Hydroxide has a charge of -1, so aluminium -4 equals -1, so aluminium must be 3. Second one, there's only one type of ligand, so it makes it a lot easier. That's hexaaqua. Now, because it's a positively charged complex, copper doesn't need to change its name, so it's hexaaqua copper. And again, water has no charge, so it means that that 2+ is coming directly from the copper. So hexaaqua copper 2. Notice no spaces. The next one is C2O4, and C2O4 is the oxalate ligand. It's the only type of ligand, so we don't need to worry about alphabetical order. And there's 3 of them, so it's going to be trioxalato. It's a negatively charged complex, so iron is going to have to change its name. So it's trioxalato ferrate. And when it comes to the charge, each oxalate has a charge of -2. There's 3 of them, so that's -6. The overall charge is -4, so iron needs to be +2. So trioxalato ferrate 2. Finally, this last one, well, we've got 3 types of ligand. We've got chloride, cyanide, and water. When we translate their names to complex, it's aqua, chlorido, cyanido would be the alphabetical order. There's 4 waters and then 1 of each of the other ones. So it's going to be tetraaqua, chlorido, cyanido. It is a neutral molecule, so cobalt doesn't change its name. So it's tetraaqua, chlorido, cyanido, cobalt, and the charge on the cobalt, well, no overall charge, water has no charge, cyanide is -1, chloride is -1. So cobalt needs to be +2 in order for there to be no charge overall. So tetraaqua, chlorido, cyanido, cobalt 2. Now, if the complex is part of a salt or part of a compound, what you need to do is look at the ions associated with it to work out what the charge on the complex would be. So if it is a negatively charged complex, it would be associated with things like sodium, potassium, or maybe even magnesium. So you need to know that sodium has a +1 charge, potassium has a +1 charge, magnesium has a +2 charge. And then from that, name the complex and work out the charge. So in this case, each sodium is +1, so the complex must be a -2. Each cyanide is -1, so the copper must have a +2 charge, because copper -4 equals -2, so copper must be +2. Remember that the name of the metal ion, not in the complex, always goes first. So the positive ions always go before the negative ions. So it's sodium tetracyanido cuprate, because it's a negatively charged complex, 2. Now here are 4, this is the final slide. Again, have a go at naming these 4 compounds this time. So we've got ions and a complex all in the one compound. Have a go, pause, and I will see you, well, you'll hear me after you have tried them. Okay, so I'm hoping that you've all managed to have a go at that and didn't just listen to me make no noise. For the first one, we have got potassium and then we've got the complex. Potassium is positively charged, so potassium comes first and then the complex name. So the complex has a -1 charge. We've got 6 chlorines, so it's hexachlorido. The complex is negatively charged, so the chromium is going to need to change its name. So it's potassium, then we have a space, hexachlorido chromate, and then we have to work out the oxidation state on the chromium. Now we know that the complex must have a -1 charge because there's only one potassium beside it. So chromium -6, because there's 6 chlorines, equals -1, so chromium must be 5. So potassium hexachlorido chromate 5. The next one, we've got 1 sodium on the outside. It's positively charged. That means the complex is negatively charged. There's only 1 sodium, so the complex has a -1 charge. So we know that positive comes before negative, so it's going to be sodium and then the name of the complex. Now the complex has a -1 charge, so the name iron is going to have to change. The ligands are ammonia and cyanide. If we look at the alphabetical order, ammonia becomes amine, cyanide, cyanido, so the amine is going to come first. We've got 2 amines, we've got 4 cyanidos, so it is sodium diamine tetracyanidoferrate because it was negatively charged. Now we know it has a -1 charge. Ammonia is a neutral molecule, so doesn't contribute anything towards that. So iron minus the 4 cyanides equals -1, so iron must be 3. Sodium diamine tetracyanidoferrate 3. The next one, well, there's 3 sodiums. Sodium is positively charged, so the complex is negatively charged, and it must be -3 because we needed 3 sodiums. So we know that we're going to write the sodium first, and then we're going to write the complex. The complex has 2 types of ligand. It's got hydroxide and chloride. Alphabetically, chlorido comes before hydroxido. There's 3 of each type of ligand. So it's sodium trichlorido trihydroxido. It's a negatively charged complex, so aluminium becomes aluminate, and then when it comes to working out the charge, the overall charge on the complex must be -3. Chloride and hydroxide both have a -1 charge, so aluminium -6 equals -3, so aluminium should be +3. So we put the 3 in brackets. Now the final one, we've got chloride outside of the complex. Chloride is negatively charged because it's a halide. That means that the complex is positively charged. Positive goes before negative, so we're going to put the name of the complex, then we're going to put the chloride. The complex is positively charged, so copper doesn't change its name. We've only got 1 ligand, it's amine, and there's 6 of them, so it's going to be hexaamine. There's 2 chlorides, so we know that the charge in the complex is +2. Ammonia is a neutral molecule, so it doesn't contribute towards the charge, so that means that the 2+ charge is coming directly from the copper. And that means that we have hexaamine copper 2 chloride. So that concludes our lesson on transition metal complexes, on coordination number, on denticity of ligands, on understanding what a dative covalent bond is, and then we spent the majority of our time going over the rules for how to name a transition metal complex. Hopefully that makes sense to you, and I will see you with the next and final video on transition metals. Thank you for your attention.